It's
Okay.
to work. Yes, floor yours.
So thank you. So yes, my name is Cyril Cayron, and I'm a scientist at EPFL in the laboratory of thermomechanical metallurgy. It is directed by Professor Roland Loger, that you see here. And this laboratory is located in Switzerland at Neuchâtel, not at Lausanne, but at Neuchâtel. And you can see on the next slide here, where is Neuchâtel? So we have also a beautiful lake called Lake de Neuchâtel, and a very nice view on the Swiss Alps here. So it's a very nice place to work. So I'm here for 1 hour more or less to speak about martensite and twins. So I will spend the first half hour to a theory, classical theory of deformation twins, and classical theory of martensitic transformation, and mainly the phenomenological theory of martensite crystallography called PTMC. And then the rest of my talk will be of my own research to try to find alternatives to these theories with simple models, art spheres. And I will also introduce more in details the notion of variance for different concepts of orientation, correspondence, distortion. We will see that. And if I have time, and I hope that I will have time, I will speak about the correspondence theories that I made recently and the use of the interaction work to predict variance selection. I will not speak about habit planes and weak twins. I'm sorry. It was in the abstract, but I will not have time to do that. So let's start by terminology, because I think it's important that we are sure that we speak the same language to avoid any confusion or any unfruitful debate. So to me, or for a lot of people in metallurgy, a martensitic transformation, it's a phase transformation in which the atoms move in an organized manner simultaneously. And there is a homogeneous lattice distortion. That is, I disagree on that. It's not necessarily a shear transformation. That's why I prefer the general term of lattice distortion. After what the parent phase is transformed into daughter phase without compositional change. There is no diffusion. So more or less, a martensitic transformation for us metallurgists means diffusionless, displacive, or military transformation. I follow Professor Badeshia's definition for that. So more or less, it's a displacive, non-diffusive, and there is a phase, there is a shape change. If you look at here, it's more or less you have different kind of atoms, round atom or square atoms. And after this lattice distortion, the atoms remain more or less at the same place, but it is a lattice that was distorted. So it introduced a shape change. And the opposite is what we call reconstructive transformation, that is purely diffusive, and there is no shape change. It means that we can form an hexagonal lattice here, as it is the case here, but then the position of the atoms cannot be traced back. It's impossible to know where this square atom comes from or where this round atom comes from. It's purely diffusive and not coordinated transformation. Be very, very careful with this terminology, displacive and reconstructive, because if you speak with a physicist or with crystallographers, it's nearly the opposite meaning. I will not detail here, but be very careful with these terms. When you have a martensitic transformation, most of the time you have an orientation relationship. Here, for example, in colors, you see the BCC martensite that is formed in iron, nickel, copper, carbon steel. And you can, by EBSD, electron backscatter diffraction map, you can measure a specific misorientation between the retained austenite in gray and the color martensite. So it is part of most of the time when we have martensite, we have this specific orientation relationship. Another particularity of martensitic transformation is that martensite has very specific morphologies. Here, it's a lath or lenticular shape with what we call an habit plane. It's a plane, crystallographic plane on which the martensite is formed. And if you here in this case, it's not the case in all martensite in steels, but in this specific steel, inside the martensite lath or lenticle, we have what we call the midrib. And if we were able to do a transmission electron microscopy to look more in details what is in the midrib, we will see an alternance of two BCC, two martensitic variants, actually. One in black and the other here in white. And diffraction condition is in black. And okay, it seems to be a detail here for martensite. We do not necessarily observe them. We observe them only in some alloys. But these transformation twins, these twin-related variants, are very important in shape memory alloy. It's what we see here. Here it's martensitic martensite form in this shape memory alloy. And you see here we have a plate of martensite, and inside this plate we see two variants. And the junctions between the variants here in yellow is called junction plane. And the relationship between these two variants is called a twin, a transformation twin. So it is the case in this alloy. Here it's another example where we see here the plates, so what we call here the habit plane. And here in between, the plane between the variants forming the habit plane is called the junction plane. The junction plane is very important for shape memory alloy. And at the contrary, the concept of habit planes is sometimes very difficult to define for shape memory alloys. For example, here it's a nitinol, it's a nickel titanium shape memory alloy, in which here we have the prior parent grains, cubic B2 grains, and we do not see really a plate. We see the variants here with the junction planes here, but we do not see planes. Or in this kind of microstructure here, it's another shape memory alloys with gold. I cannot detail more, but it's really difficult to know where are the habit planes or where are the junction planes, because here we can have the feeling that we have an habit plane here with two variants, but actually we could also have an habit plane here with other variants inside. And this fractal microstructure makes it very difficult to know, okay, what do I observe? Is it a habit plane or is it a junction plane? Okay, so I tried to introduce what was a transformation twins. Actually, they are variants created by martensitic transformations, but there are other sorts of twins. The annealing twins that are formed when you deform a low stacking fault FCC material and then you heat the material. You will create a recrystallization on grain growth inside the material, and during the grain growth, some accident on the 111 plane on this FCC material can appear. So it grows like that, and then suddenly it changes the orientation into a new orientation, and so that, and it can make it alternatively on different 111 plane. And so you create these annealing twins. They are straight, they are parallel to the 111 direction of your FCC face center cubic material. And here it's an EBSD map, an electron backscatter map. If you measure the misorientation between these two grains, it's 60 degrees around this orientation. And there are another kind of twins that are deformation twins. And I will insist more here on these deformation twins because they also result from a displacive mechanism. They are really similar to martensite, actually. And you see the difference here? Here we have straight boundaries, and here it's not straight. It's curved, it's lenticular shape. It looks like martensite, but they are twins. There are no new phases. All what you see is FCC. Here it's a copper titanium alloys. If you need to find them, you can enter in your EBSD map the special misorientation of 60 degrees, but you have to add more tolerance angle to define them. Okay, since we will do crystallography, I need to introduce here 3 types of transformation matrices. Okay, first of all, I need to define what is an orientation matrix. I told you that we have, in martensitic transformation, we have an orientation relationship. So we can encode this orientation relationship by a matrix in which we have the daughter phase here, it's a martensite. In this example, it's a rectangular centered phase. And we have the parent phase here, that is simply a square. So to define this orientation relationship, we just write the crystallographic, the coordinate of the crystallographic vectors of the daughter phase here and here inside the basis of the parent phase. So I use this notation. So it's in this orientation relationship, there is no idea of mechanism. Okay, we don't know if it's actually, if it's a displacive or reconstructive. We just encode the orientation relationship between these two phases. Now, if I know that this transformation is displacive, I can look at how can I go from here to here. Oh, and I said, look, if I take this square and I slightly distort this square to form this rhombus here, then this rhombus is the same as here, and I will form this center rectangular phase. So this distortion is called the lattice distortion, and I call it distortion matrix. Okay, I go to B gamma, that is my parent phase, to B gamma prime. Prime means distortion. But these distorted vectors here, B gamma prime, correspond to specific vector in my daughter phase. For example, B gamma prime here is 1/2 of A alpha and 1/2 of plus 1/2 of B beta. Here it's 1/2, 1/2. And A gamma prime is 1/2 minus 1/2. So I can encode this orientation, this specific link between A gamma prime and B gamma prime with alpha and B alpha by what is called, not me, it's called in general, correspondence matrix. And the correspondence matrix is always a rational matrix. Okay, this is very important to know. In general, we use the orientation relationship when we do EBSD or TEM, and we use the distortion matrix when we do mechanics, and it's rarely used, but if we were doing spectroscopy, we would use the correspondence matrix. They are nice if we are interested in the inverse transformation. Instead of going from gamma to alpha, we go from alpha to gamma. It's very simple. The orientation relationship matrix is the inverse of the first one. Okay, it's the same for the correspondence matrix. And if we need to do some calculations in the reciprocal space, okay, here it means that we work in the reciprocal space. If we want to work with planes instead of direction, we use this matrix with a star here. On the star, it's just the inverse of the transpose of these matrices here. And there is a nice relationship between the three matrices. It's that the correspondence is a orientation relationship matrix multiplied by the distortion matrix here in this. And we will use this, we will use later these equations. Okay, and let's explain with an example these three matrices. I think that most of you know how we go simply from FCC to BCC, from face center cubic to body center cubic. It's a Bain model of transformation. We take a FCC unit cell here. Actually, we take two unit cells side by side. And in the middle here, you see, we have a tetragonal centered cell here. So if we take this tetragonal centered cell here, it's quite easy to understand how we can distort it to make it center cubic cell. We just have to contract along this axis and elongate the direction along these two axes here. If you do that, you can do the calculations. Okay, we can add some constraint on the lattice parameters by assuming that the iron atoms here are hard spheres. And if you do that, the distortion matrix is actually a stretch matrix. It's a diagonal matrix here, and you can do the calculation and you get this. In general, you have a matrix that is close to identity for a distortion matrix because the distortion is never very, very big. Okay, if you can do the orientation calculation of the orientation relationship matrix here, and it's more or less a rotation of 45 degrees, okay, between this cube and this cube. It's 45 degrees along the c-axis. And okay, you have to take into account the volume change. That's why you have this factor in front of the matrix. On the correspondence matrix, okay, you look at you take these vectors and you look after the distortion. They will become this vector here in the parent phase. So for this A2 vector will become the 1, 1, 0 vector of the BCC phase. So you can get very easily the correspondence matrix. And I insist, look, here it's a stretch matrix, here it's a correspondence matrix. It is not the same. That's why when I see in some papers that people confused the stretch on the correspondence, no, it is not the same, and we should avoid the confusion. Okay, last word on the what we call shuffle. Okay, let's consider, for example, this is a parent phase. Okay, it is strange. It is a center rectangular phase, and this is a daughter phase. Why not? It is a parallelogram phase with a strange position of the atom here in the unit cell, but why not? If I look at how I can go from here to here, well, I can see that it's very simple. I take this lattice here and I apply a simple shear along this direction. Okay, so it means that for the atoms that are on the node of the lattice, it's just a simple shear. But for the atoms that were here in the center of the lattice, look, the trajectory of the atoms are quite strange. It is not a simple shear. So we call the trajectory of the atoms that do not follow the trajectory of the nodes of the lattice, we call them shuffling. And a well-known example of shuffle transformation, or at least a transformation in which there is a shuffle, it's a BCC to HCP transformation in titanium or in zirconium. We can even imagine transformation with pure shuffle. It means that we do not change the lattice. The lattice is exactly the same, and it's just the position of the atoms in the center that move. Well, it's very, very rare. The only case I know of pure shuffle transformation is the formation of omega phase in titanium niobium alloys, for example. Because most of the time, we cannot move freely an atom without moving the rest of the atoms, as it is represented here. With art sphere models, we can really understand that if we want to move this atom, we should also move or distort the lattice. Or oppositely, if we distort the lattice, we will also move this atom here. Okay, it's more or less finished with the terminology. Let's go to the theory of deformation twinning. Deformation twinning is a specific kind of plastic deformation. It is, I think most of you know that we can plastically deform by dislocations, but there is also this mechanism of deformation, plastic deformation by twinning. It's a specific shear, okay, of the lattice that restored the lattice, but with a new orientation. Okay, we shear it, and for a certain value of the shear amplitude, we can restore this rectangular phase. So to me, it's deformation twinning is really very similar to a martensitic transformation. It's just that the daughter phase is the same as the parent phase. And instead of being driven by chemical energy, it is driven by mechanical energy. We know that we have deformation twinning in metallurgy, but we should be also open to other topics, and there are also deformation twinning in mineralogy. For example, it is a well-known example of deformation twinning in calcite. With a pocket knife, for example, you can press the edge of your knife on the edge of calcite crystal, and you create a twin. Or you can press the two corners with your hand of a calcite crystal, and you create a deformation twin. So it's not specific to metals, actually. In all the textbooks I know, people will tell you that deformation twinning is more or less equivalent to a simple shear. And it's quite obvious, it's written, but I will explain in the detail why I disagree with this definition. Before telling why, I need to come back to the origin of crystallography. it dates more or less from Abe Aui in 1822, when he noticed that a crystal could be described by a pileup of what he called molecule integrants, represented here. These molecule integrants were more or less imagined as bricks, and the crystal was more or less imagined as a pileup of bricks, like a wall. So if you have this representation in mind, it's quite easy to imagine what could be deformation twinning. For example, if we take this crystal made of bricks, the motif is a brick, we can go we glide the bricks along this direction, and for a certain amount of shear, of displacement of the bricks, we can restore the lattice here. Look, this lattice here is in mirror symmetry with this lattice here. These two lattices are in mirror symmetry. It means that we have restored the lattice. So it's very compatible with shearing is really natural if you have this, if you imagine this motif as bricks. I think that's why Muge in 1988 created his model of deformation twins, and with the introduction of, maybe you know, the K1, new eta 1, K2, eta 2 notations, and with a distinction between the type 1 and type 2 twins. It is a model made of simple shear. Let me explain. We have a crystal, and we want from the crystal to know what could be the twin. I need to define the twin plane and the twin direction. So in my crystal, I need to find I need to define a unit cell. So I take 3 directions in yellow here, 3 crystallographic directions. With 2 of them, I create a crystallographic plane with a low index, for example, HKL value, okay? And I call this plane K1. It's an input in my model, okay? And the 3rd direction, it's a rational direction, okay? It's a crystallographic direction. I call it eta 2. I do not choose eta 2 randomly. Actually, what I do, I calculate the normal to the K1 plane, okay? And I take eta 2 very close to this normal. But the normal is not necessarily rational, whereas this direction is necessarily rational. Then it's exactly the model of the bricks I told you before. I know that if I apply a rotation around this normal here, I can transform this direction into this direction of the same length. Okay, so this is the initial basis, and this is the final basis after distortion. They look different, but this direction is completely equivalent to this direction. It means that the basis in yellow, the initial basis, and the basis after shear, that is this one, and this one, are in mirror symmetry position each other. Okay, there is a mirror symmetry between each other. So we have created a twin. So, and this is called a type 1 twin because I have chosen the K1 plane. So the input data is a plane K1. And the output of my model is a shear direction here. That is called eta 1. I could have made another choice. Instead of fixing the plane here, I can fix the 3rd direction, eta 2. And then, if I fix this direction, I will shear the plane K1. Okay, to create a new plane K1 prime that is not represented in this figure. And by doing that, I can calculate the image of K1 prime. I can calculate the intersection of the 2, which gives this direction here. And these 2 directions, eta 2 and this direction, are left invariant by the twinning operation. It means that the K2 plane is invariant. It means that in my model, the shear direction is the input. Okay, it's eta 2, it's the shear direction. And the output is the shearing plane, K2. And I can notice that in that case, the parent on the twin phases are related by a half turn around this direction. Okay. In the first case, type 1 twins are mirror symmetry through a K1 plane, and this is the type 2 twin. The relationship between the parent on the twin phase is a rotation it's a twofold rotation around this direction here. Okay, I know it's a little tricky. Most of the time in cubic, we don't need to distinguish them, but it's important as soon as you work in hexagonal lattices or monoclinic lattices, it's important to make the distinction between the type 1 and type 2 twins. Okay, there are, we can put in mathematics what I said. And it was done for a long time by Bevis and Crocker, for example. I will not explain here, I have no time the full theory, but it is based on the relationship between the correspondence, the distortion, and the coordinate transformation matrix, the orientation matrix that is in specific cases a rotation. What is important to me is that inside this theory, there is an important relationship that completely astonished me when I read the paper. It is here, is that you can calculate the shear amplitude of the twin without calculating the twin distortion. What we need is we just need to know what is the correspondence between the parent and the twin. And it is a rational, you remember, it is a rational matrix here. What we need in addition is the metric tensor. I will not detail, you can calculate the metric tensor nearly immediately from the lattice parameters. So you can, if it's cubic, the metric tensor is identity. Okay, so if you apply this relationship, you can calculate the shear amplitude. Okay, and from the correspondence, you can also calculate the shear direction. You can calculate also the shear plane, and with that, you can calculate the shear distortion matrix related to the twinning. Okay, I do not detail. You need to normalize the shear direction. You need to normalize the shear plane in the respective space, in the direct space and in the reciprocal space, but you can do the calculation. Since time goes, I need to go faster, so I need to show you just a brief example of application of this formula. I consider this very simple example of hexagonal packing of disk here. For example, this is my parent crystal. I apply a shear stress and I shear it into a new orientation. Actually, it seems to be a new orientation, but it's exactly the same orientation. It remains hexagonal with the same orientation, but whatever. I have applied a shear stress and I have a shear distortion. If I want to calculate the shear amplitude of the twinning, it's this distance here, d, divided by the interplanar distance here, h. And if I can do that geometrically, it's very easy. It's 2 divided by the square root of 3. Okay. Well, in this simple case, geometry gives you the answer. But I can tell you by experience that if you want to do that with a 3D real crystals, geometry does not work anymore, or it does not help you so much. But at the opposite, if you apply the Bevis and Crocker formula, it gives you immediately the result. Okay, you have to calculate the metric tensor. Here, for an hexagonal phase, it is given here. Okay, here it's -1/2 because you have a rotation, an angle of 120 degrees between these two vectors. That's why the cosine makes a -1/2, and it's a symmetric tensor. So you can calculate quite easily the metric tensor. And the correspondence matrix is also very easily calculated. And then you apply the formula, and it gives you that the shear amplitude is exactly as you have found by geometry. But here, this approach works in any cases, even the very complex ones. Okay, let's speak very fast of martensitic transformation. There is one theory that is called Phenomenological theory of martensitic transformation, PTMC, and there are two versions of it. The first version that is used by people working in steels is described here. This comes from Badeshia again. I used a lot of illustration made by Professor Badeshia. I already explained that you can go from FCC to BCC by a contraction along these two axes and the expansion along, by a contraction along this axis and expansion along these two axes. So this stretch matrix is called also Bain matrices. The only problem is that the final orientation relationship between the FCC and BCC is not what we observed. The second problem is that I told you at the beginning that the martensite has a shape, lenticular shape, or a plate shape. It means that we imagine that martensite result from an invariant plane strain, which is called encoded by a matrix P1, in which it's an invariant plane strain is exactly as a simple shear, except that we have a dilatation perpendicular to the plane to take into account the volume change between FCC and BCC. So you make your theory by, on one side you have the Bain stretch, on the other side you have invariant plane strain. And to make it coherent, what you do, you multiply at the right here by a rotation matrix, and you combine here at the right by a simple shear. Why you do that? Because you can prove that this rotation combined with Bain is an invariant line strain. It leaves a direction invariance. And it's the same here. If you combine an IPS with a lattice invariant shear, you have also an invariant line strain. So you can put that into coherency. The only thing you have to do is to guess what is this lattice invariant shear here. It can be glides of dislocation, it can be mechanical twinning, whatever. That's maybe the problem of this version of PTMC. We do not have this problem in the second version of PTMC that is very well, that is used by people working in shape memory alloys, because there is no real input in it. It's a nice theory. The equations looks like the same, but the assumptions are quite different here. We consider here it's austenite, okay? And here it's one part of austenite that will become one variant of martensite, and another part of austenite that will become another variant of austenite, of martensite. And we want that each of them have their own transformation that we can decompose by polar decomposition into a stretch matrix and a rotation matrix. Okay, but what is important is that at the interface, I should not create holes or overlap. It means that what happened at the interface should be distorted similarly by this distortion matrix and by this distortion matrix, okay? And mathematically, if you want to have this condition of compatibility at the interface, which is a junction plane here, you can write this compatibility by this equation. The distortion, you take the first distortion minus the second distortion, and it should have this form. This form is more or less the form of a simple shear minus identity. Where they called this relationship, they said that the two matrices are rank 1 connected. Okay, with this equation, you can find the junction plane. And they use also another equation to establish a compatibility between the average distortion matrix made by the two variants, AB, and the austenite. So here it's the average of the two distortion, so just a linear average of distortion, and at the end, you should get invariant plane strain equal to the P1 of the first version. Okay, these are the two main equations of the second version of PTMC. Behind that, you still have a lot of equations to solve to get your solutions. It's not so direct, actually. But it is nice because there is nearly no input parameter here. But to me, and it's my personal opinion on it, I'm not so comfortable with it. Why? Because these two versions rely on the exact value of the lattice parameters, if the results rely on it. And once you do your calculation, you realize that some part of the solution, for example, some junction planes for the type 1 twins, do not rely on this lattice parameter. So it means that you do a lot of calculation with taking into account the lattice parameters very exactly, but at the end, some solutions do not depend on the exact value of the lattice parameters. And this was already noticed by Piteri and Zanzotto, and they call it generic twins. But it is not clear why some twins are generic, some twins are not. And also that what I don't like is that some solutions are discarded. So you have to solve some equations, and at the end, okay, you said, I keep this solution because it's in agreement with experiments. On this solution, no, I discard it because it does not fit with experiments. It's not very satisfying. Another thing is that the symmetries are treated quite strangely. Okay, they are used to calculate the stretch variance, sometimes unfortunately called correspondence variance, and then they are completely forgotten. So we do not realize, we do not understand the rules of the symmetry. There are also some unexplained facts. For example, the 2 to 5 habit planes in steels is not explained by the theory. And also, if you do EBSD on martensite, you realize that actually it's not a unique orientation. Martensite is often made of a gradient of orientation. Oh, sorry for that. And in the pole figure, for example, we see some continuum of orientation inside, and this is not explained by the PTMC. The other point is that it is phenomenological because it does not describe how the atoms move. And to me, the problem it is based on simple shear. And the simple shear are not compatible with the atoms. Okay, so that's why I introduce my own research on the subject, and I will start by hard sphere models. Because we know that the atoms in the lattice are not bricks. They are not. They are more spheres than bricks. So it means that if we want to apply a simple shear to go from this position to this position, if we just imagine a simple shear model, a continuous simple shear model, we are in trouble here in the intermediate position because the interaction between these two atoms is too strong. So it's impossible. And actually, we can even calculate that the shear value will be of order of the shear Young modulus. So that's really impossible. So that's why people came to say, okay, we will solve the problem by assuming that we have dislocations to go from here to here. And not only we have dislocation, but they will assume that the dislocation creates the martensite or creates the twins. And to me, it's a problem because in that case, you have to explain where the dislocation comes from. Okay, if they create the twins, explain me where they come from and how they can be stacked regularly on planes with very specific Burgers vectors. So people try to cope with that by imagining a pole mechanism in which we, at the beginning, we have only one dislocation that turns around one lines, but this spiraling dislocation has never been observed by TM. So there is a second hypothesis that I try to introduce is to say, okay, there is no obligation for the atoms to respect a simple shear. I mean, why not imagining that the atoms, the interatomic distance here can change in the intermediate state to go from here to here? I mean, why not leaving the atoms rolling on each other? Why? And it's even more the case if you take into account that just during a martensitic phase transformation, there are some softening modes in which chemical bonding can decrease. Okay, so but if you continue with this point of view, you say that, okay, it is the martensite that creates the dislocations and not the dislocations that create the martensite. And it's not the same, it's not a chicken and egg question. Because if you go in this direction, you need to explain the dislocation to explain the martensite. And it's quite complex, I should admit, okay? There are some people that spend their part of their life on it, but okay, I don't. So I prefer to say first we have martensite, and okay, maybe if we need dislocation to accommodate the interface between martensite and the parent phase. But here the calculations are easier because I will show you, we can predict the twins of the martensite by using the interaction work. And if you adopt this point of view, in that case, you will not see martensite as it is written in textbook. You will not see that the martensite results from an interface that should move. And you will not understand some sentence telling that to get a martensitic transformation, the interface should be necessarily glissile. Well, if you adopt this point of view, you don't care about the interface, actually, if it's glissile or not. Actually, sometimes you do not even need dislocations. For example, I take an example here. Here it's hexagonal crystal, it's 2D, okay? It's an hexagonal stacking of atoms. And I can show you that I can go from here to a square stacking of atoms without dislocation. I just start to make a slight angular distortion here, okay? It's nearly a square, not totally a square. Here it becomes a square, and progressively I go from square to hexagonal packing. And at the end, if I continue to propagate the wave of transformation, I get a fully square lattice. So try to find a very specific point defect dislocation, you will not. Actually, it's more like this angular distortion is more connected to what I would say disclinations than dislocations, but it's too specific. Okay, so this is if I see a martensitic transformation, I see it like that. If I want to do calculations, I need anyway something. I need to assume a specific orientation relationship between the parent phase and the daughter phase. But in that case, what is natural to me, I would say, is to assume that in this orientation relationship, the closed packed plane of the parent phase is parallel to the closed packed plane of the daughter phase, and the closed packed direction of the parent and daughter phase are also parallel. And this is the case in many phase transformation in metallurgy. It was already known by Burgers in 1934. It is represented here in this triangle, okay? Between, for example, FCC and BCC phases, we have a Kurdyumov-Sachs orientation that respects these conditions here. Between FCC and HCC, for example, it's a transformation in cobalt, we have a Soshi-Nishiyama orientation relationship that respects this condition too. And in titanium, between BCC and HCP transformation, we have the Burgers orientation relationship that also correspond to this, what is written here. So why not trying to find an alternative to PTMC by considering that what is important, it's not the Bain distortion exactly, but it's the orientation relationship. And actually, it's not a new idea. It was also proposed by Nishiyama, that was for a very long time of his life defender of the PTMC, but at the end of his life, he came to doubt, and that's why he wrote, okay, PTMC was only a first approximation, and maybe it needs some corrections, and maybe if we need, it is desirable to introduce a more fundamental law, and maybe it is the orientation relationship. Okay, so let's follow that. Let's assume that we know the orientation relationship. And for example, here between the initial phase FCC and the final phase here that it's distorted FCC, it's BCC, I assume a Kurdyumov-Sachs orientation relationship. It's an assumption. And I also assume that the atoms, iron atoms, are hard sphere. And then I can go from FCC to BCC continuously. I just have to open the angle between the two dense directions. Here it's 110 directions of FCC phases that will become 111 direction of BCC phases. I open this angle from initially 60 degrees to 70.5 degrees. If I can do it continuously, and I can calculate the distortion matrix from the beginning. At the early beginning, it's identity, I changed nothing. And at the end, it takes this form here. But I can calculate all these intermediate states. It depends on x, as x is a cosine of this distortion angle. So I can make a movie. It's not a DFT, it's not molecular dynamics, it's simple art sphere model to make a movie of what could be the phase transformation. Okay, what is nice also is that you realize that this plane here is unrotated by this distortion matrix. And not only it is unrotated, but if you combine two variants that have this plane unrotated and that also share a common direction, if you combine two of them, you can make an average of these two distortion variants and you get an IPS. So even PTMC promoter should be happy with that. And you can calculate what is the shear amplitude or what is the dilatation perpendicular to the shear. You can calculate also the interface between these two variants, and it is a 111 parallel to 112 of the Martensite. And more or less, you can do a movie of the phase transformation with these two variants, and you have this schematic representation of what happened to go from FCC to BCC with an invariant plane here. It is not invariant by one distortion, but it is invariant by the linear combination of these two distortion variants here. Okay, I need to go fast. I will skip this part here. Okay, let's speak a little about group theory. First of all, I need to define what is a variant, because I will need that. Okay, I take this example of a square on an hexagonal face here. Parent phase and daughter phase. I don't care for the moment of the mechanism. For the orientation relationship, the mechanism is not important. With this orientation relationship, I put my hexagon like that. But actually, I had another choice. It's written here. I could put the hexagon like that. They are completely in equivalent position relatively to the square. And this is only two possibilities. I have two orientation variants. And why? I will try to explain you why. It's because, look, in this hexagon here, I can imagine that I could create as many hexagons as I have symmetry elements of the parent phase. I have 8 symmetry elements, mirror symmetry, rotation. So I could imagine that I could create 8 hexagons. But some symmetry elements here are common to the square and to the hexagons here. This symmetry element is common here. So it will not create a new variant. It will remain the same variant. And it's the same for this symmetry element here and here. So if I calculate the orientation relationship and I multiply by the left by one of the symmetry elements, I change nothing. And these symmetry elements that are common to the parent and the daughter variants here are written here. And they form a subgroup of the square. Here is the identity, here is the inversion, horizontal mirror symmetry and vertical symmetry. You can see they do not create a new variant. But if I take now these symmetry elements and I multiply by t, I will create a new variant, that is this one. And
Are you there?
I cannot change nothing if I multiply at the right by these symmetry elements. It means that all these symmetries will create a new variant. Okay, sorry for that. So I have as many variants as I have what we called cosets.
Are you there?
Of decomposition. I need a coset decomposition. So what is nice is that if I want to calculate the number of variants, I just calculate the number of simple cosets. And they are given by the Lagrange formula that is written here. Why I have 2 variants? It's because I have 8 symmetry elements of the square, and I have 4 symmetry elements that are common to the square and to the hexagons. And 8 divided by 4 equal 2. That's why I have 2 variants. I can even calculate the misorientation between the variants. And in that case, they are, okay, it's complex. They are given by double cosets. This is, an orientation is given by a simple coset, okay? It's here you have symmetry elements. It's a matrix. Here it's a subgroup of matrices, but you can take one of them in this subgroup. It doesn't matter. And you have a new, you have the orientation relationship between the parent phase and one of the variants. You can do that for another variant. And if you want to go from one variant I to a variant J, you take the inverse of the first matrix multiplied by the second matrix at the right, and you get that. And you see here, you have what is called the double coset. It's very technical, I'm sorry for that, but you can calculate the number of double cosets by what is called Martensite formula. I will not detail, but here, for example, it's a representation of a BCC in the square is in red to HCP transformation in titanium alloys. You see the hexagons here. We have 12 hexagons. Here you see the variance, and the misorientation between the variants are represented by these arrows here. And they mathematically they correspond to double cosets. And if you can combine these arrows, this misorientation, and you can make a composition table that is called the groupoid composition tables of these arrows. And this is exactly what I used to reconstruct the prior parent grains from EBSD maps, but it's another story. It was just a note here. I would like to tell you that we can do the same for the correspondence matrix, and it will be a key point of my presentation. Okay, for the correspondence, what is important is here we need to take into account the lattice distortion, the mechanism. For example, before I told you that we have this mirror symmetry here that was parallel to this mirror symmetry here. Okay, but if you take into account now the distortion, it does not work anymore, because the atoms 3 and 7 that were in mirror position at the beginning, they are not in mirror position after the distortion, okay? So it means that this symmetry elements is not in correspondence with these symmetry elements. If you look at this diagonal mirror symmetry here, it established a mirror symmetry between the atoms 3 and 1 here. And after the distortion, we still preserve this symmetry. The atom 3 is still in mirror position with the atom 1. Okay, these two mirror planes are not parallel, but we do not care. What is important is the relative position of the atoms each other. So we adopt the same approach, but instead of taking into account the T, the orientation matrix, we take into account C, the orientation relationship matrix. Okay, so in that case, what is important, okay, is that we can calculate the correspondence matrix as we did for the orientation matrix, and we can here realize that we have two correspondence variants. So we have as many variants as we have types of relationship between the parent phase and the daughter phase. We have variants for orientation, variants for correspondence, variants for distortion. And okay, we can even explain the reversibility, for example, in shape memory alloys, because if we look at the number of correspondence variants by the inverse transformation, since the symmetries that are common between the daughter phase and the common symmetry, the subgroup of common symmetries, they are the same. It's a monoclinic phase. I will not detail, but you can prove that by the reverse transformation, we have only one variant. We have necessarily a reversible transformation. When we have a group-subgroup relationship between the parent phase and the daughter phase, we have a reversibility that is obtained when you reverse the transformation. Okay. I think I will have no time to explain the correspondence theory. I'm really sorry for that, but I really would like to present the work made by some of my PhD students. So I will directly skip to the interaction work. How we can use the interaction work to predict variant selection. The interaction work is calculated by that. If you apply a stress to material, you calculate the stress value multiplied by the deformation matrix element. You apply this formula, okay? You multiply each element of the stress by each element of the deformation. You multiply them, and at the end, you make the addition between all these products. Here, the deformation is a deformation relative to the transformation. It means that it's a distortion minus identity. So it's very easy to do. It corresponds more or less, maximizing the interaction work corresponds more or less to maximize the shear, the Schmidt factor 1 for deformation twinning. Or it's also correspond to calculate the interaction work of this type when you work with Martensite, so it corresponds to the Patel and Cohen's law. So it's a very general approach to calculate variant selection that gives the Schmidt law and Patel and Cohen laws are just specific cases of this interaction work. So if you want to do that, if you have an EBSD map with martensite formed by a stress, what you have to do is to calculate, to reconstruct the prior parent grains if you have no retained parent phase. Then you can calculate all the distortion matrices of all the variants. You calculate the interaction work for all of them. And you should, in your map, you should observe the variants that have the maximum interaction work. And it's what we did here with one of my PhD students, Yunfeng Xiao, in shape memory nitinol, for example. It's super elastic, so it was maintained in bending condition. Here I have a contraction. Here I have an extension part. And you can see the colors of martensite that is formed here inside the austenite are completely different. So we can calculate them, and we can predict actually that the variants that will be formed are the red one, and the variants that will be formed are the green one. It's completely different orientation relationship. It is very well explained by the interaction work. We can do that also for another type of shape memory alloy, in which initially it was not austenite, it was already martensite. And when we apply a tensile test, we have what is called variant reorientation due to the tensile test. And we start with lath, and progressively they become blocks. And you see, initially we have a lot of colors, a lot of orientation, and at the end we have only one unique color. It means that we have formed one unique orientation. It is called variant reorientation. And during variant reorientation, here it's the degree of variant reorientation, and here it's a strain. And it fits very well with what we can predict by the interaction work. Here it's an example of the experimental pole figure on the calculated pole figure simulated. I will finish this presentation with a very specific, strange martensitic transformation in red gold alloys. Okay, I work in Switzerland, also we work with watch industry, we work on red golds. And we were contacted by companies that wanted to understand why when they make some very long red gold bars, some meters long, they leave the bar a few days at room temperature, and then the bars becomes wavy. And they wanted to understand that. So I suppose that it was an effect of the phase transformation. What is a phase transformation in these alloys? We start at high temperature by a FCC disorder phase in which you have copper and gold atoms that are on FCC lattices, but completely disordered. And we can, if we quench it at room temperature, we preserve this metastable FCC disorder phase. But if we leave a long time at room temperature, or if we heat the material at intermediate temperature, we have an organization of the copper and gold atoms with a lattice distortion. Okay, we have a contraction along this axis and a slight extension along this axis. It is a tetragonal phase with a C on A value lower than 1. We start by very close, value very close to 1. And if we leave time on time, we organize the atoms and we finish by this C/A values. To check this hypothesis that it could be orientated variant selection, exactly as in martensitic transformation or exactly as in shape memory alloys, we maintain in bending condition a red gold bar that was initially quenched, fully disordered, and we put this device in a furnace to activate the diffusion and to activate, it is strange, but to activate the martensitic transformation, I call it like that. And we form this variance here, this lath here. And you can see the difference of colors, and it is due to variant selection. Here, it's a contraction axis, the contraction part of the bending sample, and we have the C-axis that is parallel to the X. And here, it's the reverse. That's why we have a change of color. So it was a kind of proof that even if it's order-disorder diffusive transformation, it is also a displacive transformation. And if we look by TKD, we can see that we have a lath inside lath. It's a fractal representation, exactly as in a lot of shape memory alloys. And I will finish by that. We also notice a very, very strange effect, is that if we initiate the transformation, we put the thin foil into this ring here. We put it in the furnace, 1 minute to initiate the tetragonal transformation. And then we remove the thin foil from this ring. And we have this shape here. It means that we are just at the early beginning of the transformation. The C/A ratio is close to 1. Then we do nothing. We just put again, without any stress, this thin foil into the furnace. And without any applied stress, lonely, it continues to roll on itself. And why it is like that? It is because we have formed, we have martensite nearly everywhere, but with a very low C/A ratio, very close to 1. And when we continue the transformation, since the variants are already there, even if there is no force, they continue to grow, and we continue microscopically to see the distortion. And it's very surprising, but you can even generate a force by that. Okay, we start with a slightly martensitic state. And if we continue the transformation, we can displace a load here, as it is represented here. So I'm finishing here by the conclusion. I skip the correspondence theory. Okay, it doesn't matter. The conclusion is to say, okay, I'm sorry to tell it like that. Atoms to me look like more spheres than bricks. So theory of deformation twinning or martensitic transformations that would be based on simple shears to me are condemned to remain phenomenological forever. If you used polar decomposition to extract the stretch tensor, okay, you can do that. But please do not put at the trash the rotational part of the distortion, because it is important. And why doing that? Actually, I do not understand why we need to do polar decomposition, or why we are so attracted by the stretch tensor. I'm thinking phase transformation as a glissile interface is strange to me. It's the transformation progress that makes it think that the interface moves and not the opposite. We can use angular distortion matrices. They are quite adequate for art sphere models. And okay, I skipped that part, but I wanted to stress that the correspondence matrix and the symmetries of the parent phase and daughter phase are very important. What I wanted to show you is that it's possible to calculate the junction planes just by using the correspondence matrices, exactly as Bevis and Crocker did for deformation twinning. We could do the same for transformation twins. We do not need the long and complex PTMC calculation to do that. But if you are interested, please contact me. Okay, it's what I wrote here. Okay, and we can predict variant selection on the change of texture by using the interaction work. And I finish my presentation with this very exotic case of a transformation that is both order disorder, diffusive, and displacive. It is in red gold. It is not benite, and it shows a transformation with amplification effect. And I wanted to finish with that. So thank you for your attention. And I hope I was not too long.
Thank you very much for this wonderful presentation.